Looks like it works.
Move my blue pointer again. And then I'm gonna move my blue pointer again. And then traverse through all the ones. Since my yellow pointer is still at a 1, I'm just gonna ignore all the ones the blue pointer is pointing at. And I see a 3, so then I'm gonna update my yellow pointer. And I see a 4, I'll update it, and I see more 4s, but that doesn't matter. So I'm gonna return 0, 1, 3, 4 with a new length of 4. So that's how basically how we're gonna do it. 2 pointers, one, they traverse together in an array and see if certain elements meet a condition. Okay, obviously what I did was unidirectional, as in we have 2 pointers both moving from the left to the right, but what we can do is we can also have a pointer from the left and one starting from the right and meet in the middle. For the sake of time though, we will not be talking about this method in this workshop in detail. You can just think about it when and how you use either pointer. But yeah, okay. Okay, so that was for arrays / vectors, but now we can think about how we can utilize it for linked list. Again, it's sort of vague, so we're just gonna go directly to the problems. So basically, it's a pretty long problem, but basically what it's saying is we have to check if the list is cyclic. So if there's a cycle in the linked list, how we do it? Ideas? I'll give you another 10 seconds. Think about it. Okay, the crowd is a little responsive today, but it's okay. We'll power through. Okay, so we have 2 pointers. Let's call it fast and slow for reasons I'll tell you later. But let's look at this example linked list first, right? So we have 1 pointing to 2, to 3, to 4, to 3, to 4, because it's cyclic. So it's 3 to 4 to 3 to 4. It's never ending. So what we can do is have a pointer that moves faster, that's the fast pointer, and a slow pointer that traverses through every element. So it's something element.next equals, I guess slow equals to slow.next, and then within the loop, well, fast is equal to fast.next.next. So then the fast one will be we'll be visiting every other element. So 1, 3, 3, 3, 3, 3, 3. And then slow will be traversing through 1, 2, 3, 4, 3, 4, 3, 4. So what we can do is, okay, so basically a visualization is we'll move our fast pointer first. So it's at 3. And then we'll move our slow one. It's at 2. Well, my computer's not working. Give it a minute. That's kind of awkward. Okay. Okay. So we moved our, oh my God. Bro. Okay. Okay, but you got the idea because I talked about it, I'm pretty sure. And then for now, you can look at the slides via the link while I wait for my computer to load. Ooh, okay, so I guess it's a mistake on my end. So then slow would move to 2 first, which I didn't show, and then fast would move by 2 units again, so 3 to 4 to 3. So it's at 3, and then slow will move to 3, right? And then what we're gonna do is fast is gonna move by 2 units again. So 3 to 4, so it's still at 3. And then slow is gonna move to 4. And then fast is gonna move to 3 to 4, so it's still at 3. And then slow is now at 3. So then they meet, so we can conclude that the cycle is cyclic and it's return true. Otherwise, if they never meet, then it's false, right? So then the big O of this would be O of 1 for time and O of n for time and O of 1 for space. So that's really convenient. That's why we like to use 2 pointers. Now a quick review on binary search. So with 2 pointers in binary search, how can we combine it, right? What's the best way, best time to use it? Well, here's an example problem again. So last quarter we talked about 2sum, which is like finding 2sum that sum up to the ideal summation. This time we're gonna find 3 elements that do the same thing. So that might be a little bit harder, right? You're like, oh my God, no, it's 3. I don't know what to do. Don't really know a data structure. Worry not, we can still use a 2 pointer. But before that, we see that our ideal sum is 0, right? So then that we can have a little, we can be smart about it and just first sort it, right? Okay, it's sorted. And what we can do is we can then use binary search with 2 pointers. So what happens is, what happens is if I have, if say I want to traverse through this array, so this is like a really short pseudocode for you to understand. But say if I want to traverse through the array and I have I pointing at array index I, and I define my left as the one directly left to my index and right as the one at the back, what I can do is sum up these and check the sum of it. And if my sum is positive, that means that I have to move my left pointer, right? I have to move my right pointer, right? And if it's negative, then I know that it's 2 negative. So I'll just move my left pointer. Can I get it? Okay, we'll just step through it. So then we have -4, -1, and 2. What we can do is, so it's 2 negative, right? It's -3. So we'll move our left pointer by 1. So now it's negative, still -3. So we'll move our left pointer again. Now it's -2, still 2 negative. So now it's -1, still 2 negative though. So we'll just increment our I. So now we're, well, okay, so now we're at negative index 1, -1. And our left is 1 beside it, so also -1. Oh, okay, so they sum up to 0, which is already good. So we can just return that, okay? And then, yeah, let's ignore that because I was stupid. Okay, so now we can talk about sliding windows, which is our last technique. Sliding windows is, we usually use it to deal with a sub-range for linear data structures. It's usually arrays or strings because we are trying to, find a sub-range, say like characters or say numbers. So yeah, so what happens is we have a window, right? So we are looking at a number of elements at a time, and we just traverse through the array. So again, let's just look at problem directly. I think that would be easier to understand. So then if we're given a string S and we want to find the length of the longest substring without repeating characters, how will we do it? Okay, this time I'm gonna wait till you guys reply to me, or else I'm not gonna talk. I'm kidding. Please just talk to me. Or not. So sad. Okay, maybe not. Okay, maybe you guys are shy. Okay, fine. Okay, so, oh, that is a really good idea. Okay. That is sort of what we have in mind, except I am starting. So what you said is on the edges. What I want to do is I start, I have a unidirectional pointer just because I like it better, but that's a really good idea. Thank you so much. Thank you. Okay, so what I have is a left and right pointer pointing at index 0. What I can do is to traverse my right until, okay, so what I can do is to have a hash map that stores the count of my elements that I'm looking at right now. So I have my right pointer pointing at A right now, index 0. So that has a count of 1. And then B also has a count of 1. C also a count of 1. And then A now a count of 2. That's bad because we don't like repeating characters. So what we can do is to decrement our left pointer, increment our left pointer until the condition is not satisfied. So we're decremented, and then the count is revised to 1. So that's good. So we'll increment our right again. So B has a count of 2. That's bad. So we're decrementing our B again. Oh, left again, and that fixed it. So we're happy. And then we'll increment our right again. So that's good. But except our C, the count for our C is 2. So we don't really like it. Move our left. So that's good. And then move our right. Good, except our B is also double counted. So we're a decrement. Except this time, the B is still 2. So we'll decrement again. Right? Okay, CB, we like it. Except not really, because our best count was 3. But it's okay. We'll keep going, right? Maybe something good will happen. Okay, we'll increment our right again. Oh, they might. Okay, I was stupid, but we'll increment our right again. And then decrement our left because we double counted B, and then decrement our left again. So this is okay, except it has a length of 1. So we'll return our best result, which was 3, back in A, B, C. Okay, so that was probably a lot. So we'll take a 5 minutes break and we'll see you later. Okay. So after the heated debate, I guess, we'll come back. So a quick review before we dive into questions. Remember, this is how you should be approaching technical interviews. So basically, you have to first repeat the question in your own words, so they know you're smart and can read. And then the second one is you have to ask for clarifying questions, check for edge cases and assumptions so they know you're thinking. And then the third one is to use more examples to test your to check for the question, because sometimes in a discussion you'll realize something more. And then the fourth one is to actually brainstorm the solution and consider their time-space complexity. And then after talking with your interviewer, you can then start working on your code and then test it. Okay, so with that in your mind, let's go through a warm-up problem first. Really interesting warm-up problem. Okay, so if we're given non-negative integers and they present at coordinate IA1 and I0, we have to find a line that basically, together with the x-axis, contains the most water. So basically what that means is we're given an array of ints, and array of ints as the y coordinates, and then the x coordinates would be their index. And we have to find the container that can contain the most water, as in the area is the biggest. And then you might think, oh, what if, I slant the container, then I can contain more. Well, It's given that you cannot slant the container. And you might think, ooh, what if the numbers are negative, or what if, can I have floating points or something? Well, it's also given that n is non-negative and integers, so that we don't have to think about. So now we can think about the real test cases and how we might solve it. We can just look at the sample input and outputs right now for now. So if we look at 43214, then I'm sorry, I don't really have a visualization for this, but if you visualize it in your head, we have a high 4 and then 3, 2, 1, and then the high 4 again, right? So if we have 4 to 4, so then at the edges, right? So the height is 4, they're consistent. And then my width is 0 minus is 4, because you can count, right? So then width times height, that would produce 16. And then we can look at other numbers, say 4 and 1. So then the leftmost to the second rightmost. 4 and 1, obviously we can't slant the container, so the most we can do is 1. And our width would be 3, so that would produce an area of 3. Keep going, and then we'll realize that the best is 16 when we do the edges. If we look at the second example, it's 1, 2, 1. So your first thought might be, ooh, let's do 2 and 1, because 2 is, better. Well, if we look at it, 2 and 1, the height difference is, there's a height difference, so we can only go for 1. And then the x-axis will produce a unit of 1, so that's 1 area unit squared. Whereas if we do the 2 edges, then the height is still 1, but our width is expanded, so that's a 2. 2 times 1 is 2, so that's actually better. And then 1 versus 1, that's pretty obvious that it's 1. So how can we approach this problem? What do you think? No? You're willing to talk about pizza but not give me an answer, really? I'm kidding. What's that?
Maybe like a hash thing. So like you can store each of the heights that appear, and then when something appears twice, you can check if that could be a maximum.
That is really good. Okay, so hash map would give us a space of O of n, right? Can you think of any other way to reduce the space complexity so that we can have a more optimal? Yes, the hash map idea works. I think Felix was talking about it. But can you think of some other ways so that the space complexity is optimized? Or is it optimized already?
Can we try a dynamic programming approach?
You gotta specify, I guess.
Okay, let me think about it.
Okay.
Yeah, try to keep in mind that we're talking about like these advanced array techniques. So that's probably a great place to start, is a couple of the techniques that we just talked about.
It's really close though. Just think harder about it and you'll get it.
We can do we can have a pointer in the front and in the back, and then because intuitively you want to maximize both width and height. So if you start on either edge, maybe you can look for maximum width, and then as you iterate, I guess you can check for, I don't know.
Yes, Good job. Okay, so we're gonna actually start coding now.
Wait, just a
Uh,
quick. There's a raised. Manek, did you raise your hand?
Oh.
I did, yeah. So, kind
Oops.
of like, I guess, feel like this idea more concrete, I suppose. I was like thinking the same thing. You could have a pointer on either end, because like you basically want to maximize the width and height, as you said. So you could have a pointer on either end, and then like at each step you bring a pointer closer to the middle, and such that like whichever pointer's next step would increase like the height the most. So like, say if you move the left pointer towards the middle, you'd come to a line of like height 3. If you move the right pointer towards the middle, you'd come to a line of like height 4. Then you would choose to move the right pointer first, because it's more. And you would just keep doing that until both pointers reach each other, and then you've tried everything, or everything worth trying.
Good job. Y'all are really smart though. You like sweet pizza. Okay, so we can start coding right now. Basically, just what you had in mind. You didn't see this. I'm gonna delete it. That doesn't count. Okay, so what we can have is to have a max area, right? So we have an int that stores the max area. And oh my God, it's so slow. Okay, never mind. This is pathetic. Okay, I'm just gonna Control Z so you can see my code. And then I'm just gonna talk through it because yeah, my computer's now is working against me right now. But basically what you guys had. So you guys are really smart. Well, okay, it doesn't even let me Control Z. Okay, but the idea is basically what Manic had. So we have I guess in more detail, we have an integer that stores the max size for which we return. And then we have 2 pointers, one to the very right, one to the very left. Oh, it's back. Okay. And okay. One to the left and one to the right. And while they haven't met, I will calculate the area by comparing my current area to the new area that I have. So the difference the minimum between the 2 pointers, that's my height, and then the width would be my right pointer minus my left pointer. That would indicate the x-axis, right? So what Manic had in mind, if my left pointer is higher than my right pointer, then it would be probably better to decrement my right pointer since it's smaller, so we don't really want that. Otherwise, the left pointer is probably smaller, so we'll increment that. And so we will then find the most optimal solution and return it. So the big O of this would obviously be O of 1 since we reduced it to pointers instead of using a hash map. And then the space complexity. And then the time complexity would be O of n since we are still traversing through the whole array. But okay, and solve another question. Oh my God. Bill, do you want to take over?
Sure, I will quickly take over for a sec while Katie restarts. But I guess, Katie, were you done with that question? Do you have anything else you wanted to mention?
Yeah, it's basically done.
Okay, cool.
Except testing my code, but I just want to say it works. Okay, I'm gonna be back.
Yeah, for sure.
Okay.
Cool. So we're going to poll on how you thought that question went while Katie is gone. So yeah, feel free to fill that out. So let us know how you found that question. We can calibrate future questions. Okay, great. Looks good. I think in this case, we can actually get started with Arjun's practice problem.
Okay, sounds good. I think I'll just share my screen. Okay. Give me a quick second. I think someone just joined, so I'll drop the slides in the chat again.
Sounds
There's the
good.
link. Okay. Yeah. Okay. So I shall head to question. Okay. So this is the problem, and it's basically we're given a string s and an integer k, and we want to return the length of the longest substring of s such that the frequency of each character in the substring is greater than or equal to k. So for the example, if you have the string ABA BBC and k is 2, the output will be 5 since the longest substring is ABA BB. And each character in that substring is repeated at least twice. And so that's valid. You can't add on the C because the C only appears once. So the longest substring where each character appears at least twice is the length of that substring will be 5. And similarly for the next example, if your string is AAABB and K is 3, the length of the longest substring such that the frequency of each character is at least 3 is 3 since the string is AAA. Okay, so that was a lot of letters and numbers. So is the basic framing of the question clear? And as we sort of go through our checklist again, does anyone have any questions or clarifying, either clarifying questions or assumptions that you might make while solving this problem? Feel free to unmute yourself or type your questions in the chat. Okay, so there's, yeah, I think it's mostly pretty clear, and that's understandable. One question that I did have, perhaps theoretically, would be like, can we assume that only standard English letters will be used? And the answer from the hypothetical interviewer could be yes. And even if they were to say no, we could potentially find modifications around that. So for now, we can assume only standard English vowels. Okay, so we had a couple of examples. And so I think a good place to start is always thinking of the simplest possible solution to a problem and its time and space complexity, and then trying to make improvements based on that. So if we have a string and we want to find the longest substring that follows some constraints, what is like the most simple solution, the most kind of just, let me just, if I had infinite computing power, this is what I would do solution that you can think of. And again, feel free to unmute yourself or just type it in the chat. Yeah, so sliding window is actually, I guess, I mean, if that's the simplest thing that you can think about, then honestly, that's great. And that's a great place to get started. But so we'll get to that in a minute. But at the moment, for the most simple, just check every possible substring, absolutely. And just find whichever substring it follows all of your conditions and has the biggest length. So if you were to look at every possible substring of this string, and you were to find the longest string that meets a particular condition, what would the time complexity be of doing that? Of just looking at every possible substring, seeing if each character in that substring occurs at least k times, and then accordingly finding the length and seeing if that's your maximum one. So what would the time complexity be of that algorithm? Okay, so this is so n possible starts. Oh no, no worries, it's absolutely fine. So n possible starts, n possible ends, n max length of substrings. Okay, to be honest, I thought it would be n squared, but yeah, I think it would be n squared to just get every possible substring of a particular string. But I think I'll possibly check back on that right before we're done. Okay, so that's a place to start. So we have this kind of baseline that we know we want to try to do a little better than. So sort of moving on from this kind of brute force, just look at everything kind of solution, are there any other ideas you can think of? And we kind of sort of went over, the idea of a sliding window was thrown out there. So if you were to have a sliding window, what would that kind of look like? And we take like a few 30 seconds to a minute to think about it. And again, feel free to discuss as well. But yeah, what could a potential sliding window solution look like? Okay, no worries. So I guess what I'll do is I'll kind of just talk through like what my idea was of a sliding window. So if we have this string here, ABABBC, our window has two ends, excuse me, like a left end and a right end. So we need conditions to kind of increment or decrement to shift our window along the string, basically. So that condition is basically conditioned on the validity of a substring. So a substring is valid if every character in it occurs at least k times. So that's something to just keep in mind. But again, our basic question is, when do we want to move along the string? Or what condition do we want to use to move the boundaries of our windows as we check along the string? Oh yeah, this condition was a little tricky. It definitely wasn't the first thing I could think about, but in the solution that I'm about to present, what we're going to see is that a condition that we're going to use to move along our string is to have a particular number of unique letters we're expecting our candidate strings to have. So we want to make sure that we do move along. And so our condition for either moving the right end or the left end of our window will be the number of unique letters that we have seen so far. And basically whether those letters appear at least k times or not. Okay, so that idea is a lot. Does anyone have any questions about that idea before we jump into the code? It should be a little clear once we write some code. Okay, so I guess we'll get started. We're going to need some data structure to keep track of how many times we've seen each letter when while we're counting. So for that, I'm just going to use a vector of length 26 and set all of its entries to 0. So I'm going to call that a vector of ints, and it's going to be called count of char. And this syntax that you're about to see just means it's a vector of length 26, and each entry should be initialized to 0. And I'm also going to declare a value called maxlen. And this is going to be the final value that we return, the maximum length of a substring that follows the conditions. Make sure you set it to 0, otherwise it could have some garbage value. And when you do comparisons, it'll go haywire. Okay, so now we're going to finally get into the constraint that I was talking about a few minutes ago. And basically, what we're going to do is we're going to fix a number of unique letters that we're looking for. And then what we're going to do is, for each possible number of unique letters, we're going to find the longest string that satisfies the condition that we're looking for. So in the English alphabet, the minimum number of unique letters a word can have is 1, and the maximum number of unique letters a word can have is 26. So that's going to be our outer loop condition. We're going to fix the number of unique characters. We're going to say, okay, in this iteration, I'm only going to consider words that have however many, like 1 or 2 or 15 or however many unique letters. And according to that, we're going to perform our sliding window and do that. Okay, so I'm going to declare an int called num of unique letters. And another, I guess, life pro tip, it's always a good idea to have super expressive variable names so that you know what you're doing. Okay. So now what I'm going to do is I'm going to declare my window pointers and a couple more values that we're going to see in a minute. So I'm going to say int left is 0, right is also 0. So these are the two boundaries for our window. And then what I'm going to say is we're going to keep track of the number of unique letters we've seen in our window so far. So I'm going to call that unique letter counter. And we're going to keep basically comparing unique letter counter and number of unique letters we've seen. Okay, so unique letter counter. And we also want to keep track of the number of letters in our window that have appeared k or more times, because at the end of the day, that's the condition that we need. We need every letter that appears in our window to appear at least k times. So we're going to call that letter appears k or more. And I'm going to set that to 0 initially. Okay, so another quick check-in. We've coded up a sort of skeleton. We're about to jump in to the actual kind of the meat and potatoes, or the pineapple and the pizza for this particular question. So does anyone have any questions about the approach at a high level? Now would be a great time to ask. Otherwise, I shall continue on my way. Okay, I don't see any questions, so I'm going to continue along. Okay, so what I'm going to do is I'm going to make sure that our vector where we're counting how many times each character occurs, I'm going to ensure that that vector is full of zeros. So I'm going to use fill. Oh, it's typing that in, in the Zoom chat. Okay, so we're going to fill, and I'm going to fill count of char. Oh. Okay, so what fill does is basically it says, I'm going to fill in between this iterator and this iterator with this value. So it's going to fill count of char with zeros. Okay, so now we're actually going to use our window, and I'm going to say while some condition, keep doing some stuff. Okay, so the two conditions for my window is that I want the right pointer of my window to remain in bounds. So right should always be less than s dot length, so that when we use when we access the index of right, it's always going to be valid. And the second condition for my window is that I want left to always be less than or equal to right. Otherwise, my left window will go to the right of my right window. And that's going to make the whole house collapse, I suppose. Okay, so here we go. So I'm going to make sure that left is always less than or equal to right. Okay. So now what I'm going to do is I'm going to talk about that condition that that I kind of alluded to earlier. So this is where we're going to decide on what direction our window is going to move in. So if the number of unique letters that I've seen is less than or equal to the number that I'm expecting on this iteration, I'm going to keep expanding my window. What that means is if unique letter counter is less than or equal to number of unique letters, I'm going to do some stuff and eventually end with right plus plus, because that's how I expand my window. Otherwise, what I'm going to do is some stuff and left plus plus, because I'm going to be contracting my window. Okay, so when I do want to expand my window, before I just start expanding, I want to do some checks. So first of all, we want to get the current letter and increment its count in count of char. So if I have letters, so a character, a lowercase letter character, so a lowercase a lowercase b, or whatever, and I want to get its index in the alphabet, what you can do is you can subtract the character a from it. So it's going to look something like this. So int index is equal to the string sub right minus a. And I feel like it's syntax like this that gets computer science majors clowned on by math people, because they're like, you're literally subtracting a letter from a number. Like, this doesn't make sense. But I mean, it works. So so basically what this does is it's going to help us find the index of the current character in count of char. Okay, so I'm now going to say count of char sub index plus plus. Now, before I just expand my window, I want to do a couple of checks on the value that I just incremented. So if the value that I just incremented is 1, it means that I've seen the current character for the first time in my window. So that means that we've encountered yet another unique letter. And so we'd want to increment the count of unique letter counted. So I'm going to say if count of char sub index. So this is nothing but the value that we just incremented. So if this is equal to 1, what I want to do is I want to increment unique letter counter. Okay, now we're not just checking for unique letters, we want each letter to appear k times. So if the value that I just incremented is k, that means that I can increment, that means that another letter now appears k or more times. So we can increment the counter that we had for letter appears k or more times. So if count of char sub index is equal to k, what I'm going to do is I'm going to say let it appears k or more plus plus. And finally, since we're in the stage of the loop where we want to expand the window, I'm going to say write plus plus. Okay, so when we're expanding the window, we're looking for new letters that have appeared, so new unique letters, and we're looking for letters that just appear k or more times. So when we want to shrink the window, we're basically going to do the same thing, but in reverse order. So I'm going to, so in the else block, I'm kind of going to do some similar stuff. So I'm going to get the index. And I'm going to decrement its counter, since what we have done is we have just basically removed it from consideration. Okay, so now what we saw is earlier when we were expanding the window, we were looking for characters that appear for the first time. But now what we're going to do is we're going to look for characters that disappear. So if a character disappeared, it means the count is going to be 0. And that means we have lost a unique letter. F's in chat for our fallen letter. Okay, and the other thing is, if a letter's frequency becomes k minus 1, it means we no longer have a particular letter appearing k or more times. So we can decrement that. And finally, left plus plus, because we are in the stage of contracting our window. So left plus plus would move the left pointer closer to the right pointer, thereby contracting our window. Okay. So now we're finally done with all of our window stuff. So what we want to do is we want to actually check if our window is valid. So in what case do we have a candidate string? That is, how do we know that our particular string follows the condition of the frequency of each character in the substring being greater than or equal to k? Okay, again, feel free to unmute yourself or type something in the chat, or if you have a question, feel free to ask. But okay, what does it mean to have a candidate string? So in this particular iteration, what it means to have a candidate string is that every letter that appears uniquely, so unique letter counter, will be equal to the number of letters that appear k or more times. So basically, unique letter counter, that unique letter counter will be equal to letter appears k or more. Now, apart from this, since in our loop, we're only looking for a particular number of unique letters, excuse me, we want to add in that constraint as well. So we're not only looking for every string in the world where the number of unique letters is the number of letters where each letter appears k or more times, but we also want to impose this additional constraint so that our sliding window is coherent and makes sense, and we don't kind of just expand the window forever. So I'm going to say unique letter counter should also be equal to number of unique letters. Okay, so if it is, it means we've hit a candidate string. So in this case, we want to check max len. So max len is going to be the max of its existing value and right minus left. Okay, so once again, a lot of kind of just logic flying around, I guess. But this update step is, I think, pretty straightforward. We're just making sure that we only want maximum to be the max of its previous value and our current candidate string. To check if our current candidate string is a valid candidate, we want it to have every unique letter appear at least k or more times. And we impose the additional constraint for our loop that the number of unique letters should be a particular value, which is held in number of unique letters. Okay, so once again, that was a lot. But once we're done with this, we've basically done everything that we need to do except return max len at the end of the function. Okay, so I think we're basically done coding. Before we jump to writing a test case and running it, are there any questions?
Is there a way for us to view this code?
Yes, we're planning.
Yeah, so we are going to publish the code on GitHub soon. We'll probably have it done by next session. So by my next session, we'll unveil the GitHub.
Yeah, we're planning on having solutions and some kind of explanation or annotation or something along those lines. So yeah, stay tuned. But in the meanwhile, I'm going to fire up these two test cases that I had on the DL. Okay, so the longest substring of AABB, where k is 2. Does anyone want to just type out the answer in chat? So what we're expecting for this? So the longest substrings in AABB such that each character appears at least twice. Thanks, Katie. Yeah, it is 4. Since each character appears twice. And similarly for ABA, BBC, we want each character to appear twice. And this was, I think, one of the stock examples, but it's going to be this, so 5. So we should get 4 and 5 when we run this. Alrighty, so we did get 4 and 5. That's always a good sign. I think it means we are probably closer to being correct than we are to being wrong. But yeah, that's basically it. So always a good idea to think about the time complexity and the space complexity of the solution that we just came up with. So does anyone want to take a stab at the time complexity of this? Okay, so we have this loop that's running 26 times. And each time that it runs, we're basically iterating once over the string. So until basically we fall off on the right or until the left reaches the right. So what that means is that this inner loop is basically an O of n operation, and we're going to do that 26 times. So the overall time complexity will be of the order of 26n, where n is the length of the string, but you can drop the 26 since that's just a constant. Okay, now for the space complexity, we're not really using any additional space other than this constant size vector, a bunch of other doodly little ints. And so it's a constant space function. And so you can see how we kind of got from this baseline brute force, just like solution of which was of the ordered n squared, and we've whittled it down to something that is of the ordered n, and that's always a good sign. Okay, so I guess that's mostly it for this question. I think we can hop back onto the slides. Katie, do you want to take us away? I can continue sharing, to be honest.
I forgot I'm muted. That'd be great. Thank you. Let's go to the next slide. The previous one. The patterns. Yeah. Okay. So a quick summary. We use 2 pointers when we're iterating through a linear data structure. Sorry. So when we're iterating through a linear data structure until one or both of the pointers hit a certain condition. It's vague because that's why we can generalize it and use it in many different problems, right? And similarly for sliding windows, it's like 2 pointers except for dealing with subranges, also in linear, ordered, and iterable arrays. Ordered, I just mean it is just there. But sorted, I mean, for binary search, I mean it's either ascending or descending, whereas ordered, I just mean it has a sort of order, like it doesn't change every time we do something. And for fast and slow, we can use it to check for cyclic linked lists and arrays, and we can also use it for when dealing with linked lists that whose length we don't really know. So we can say, for example, we're dealing with the middle of a linked list and we don't want to traverse through it twice, then we can have a fast pointer and a slow pointer maintaining a certain distance and deal with that later. Okay, so next slide.
Oh, and before we move on, we're gonna poll for how you found the last problem. So feel free to fill that out while Katie concludes.
Okay, so basically you've learned a lot. Thank you for coming to this workshop. We don't have a workshop next week, but we have one the week after that because you have midterms and we're nice about it. So yeah, okay. So remember to fill out the forms and the last slide, Arjun slide. Okay, remember to fill out the feedback forms so we know how to improve. Thank you for coming again. And yeah, thank you.
Okay, we have a couple of questions. Or a couple of people who had questions with the explanation. Feel free to
not leave.
feel
No. Okay. Was that too hard? Okay, maybe it's a lot of, because okay, my example